Welcome to day 12 of the macOS and iOS Security Internals Advent Calendar. Today we were looking at mandatory access control in the XGNU kernel. So what is the mandatory access control framework, the Mac framework? Basically the XGNU Mac framework is based on the trusted BSD Mac framework. And the idea is to implement basically mandatory access control hooks throughout the whole kernel, sometimes even in kernel drivers. And in macOS and iOS, basically most of the security features are somehow rooted in this, like the sandbox is rooted in this, the entitlement checking is rooted in this, code signing by itself is rooted in this, and when we talk about something like zip, many of zip features are also basically implemented by having certain Mac checks. So because this is all based on something coming from trusted BSD, there has been research published for these Mac framework. And the figure below is basically from a research paper from Robert N.M. Watson, who was one of the first authors of the trusted BSD Mac framework. The picture is very interesting to show you the concept of the Mac framework. So when we look at this here, we can see we have our userland processes. They make system calls. This might be system calls, this might be Mach traps in the case of iOS and so on, or Mach API or something similar. But in some way they issue a call to the kernel and tell the kernel to do something. In this case, the process wants to manipulate a file, so it talks through the virtual file system layer. And now the idea is that the file system layer had now a hook in there that asks the trusted BSD Mac framework, should I allow this operation or not? And based on the information it gets, it should make the decision. But the problem is the framework itself is actually stupid. It has no idea what should be allowed or not. For that it needs policies that needs to be loaded into the framework. And this here symbolizes two compiled in policies and one loadable policy via driver or so. And while all these names here make no sense in the context of macOS and iOS, they actually make sense in the way they work, because the same feature exists basically in XGNU and therefore in macOS and iOS. So you can have built-in policies and dynamic loadable policies. So the good thing is, or the good news is, that the Mac framework is part of the main kernel source code. And because it's everywhere, Apple has actually not stripped it out as security obfuscation. No, the Mac framework source code is fully available the moment Apple releases the source code. The policies, however, are a different topic, because the policies, they come from drivers, and all the security drivers from Apple are basically closed source at the moment. So the policies are not available as source code. And both macOS and iOS ship actually with a bunch of these closed source policy modules. So if you look at the XGNU source code, you will find the Mac framework integrated all over the place. Usually you would find an if config_Mac framework, which is always the code that is responsible to do some Mac framework checking. And in this case, we are in the mmap system call, and they wanted to harden the map_JIT flag, which allows to have one readable, writable, executable memory area in a process. And obviously, you don't want to have this in all processes on something like iOS or so. And this is why they added this Mac hook here. And so what we can see here is there's a call out to something called mac proc check map anon. The name basically gives already everything away. We are checking an anonymous mapping, and that's exactly what we're doing here. We have an mmap of an anonymous mapping, and as you can see here, it gets the process that is doing it, the address, the size, the protection level that we request, some flags, and apparently we can give back a maximum protection. Yeah, so how does it look like under the hood? When we drill down into this, we will find, first of all, we first zoom on this area, because the good thing is all of this here is of course also part of the open source code. We are able to look into this, and the way you read this here, I already said it partially, but what you need to realize is that these functions, when they return basically a Unix like error code, an error, and depending on this error code, this will be allowed or not. And so an error is usually saying no, this is not allowed. And whenever here an error happens, then this will error out the system call usually, and here is an inval or einval, or however you want to pronounce it. And that's basically the case that usually happens when there's a check to the Mac framework. It says, oh, there's an error, and then the system call will just tell the user that there was an input error. Okay, let's drill down into this function. This function could look like this. There's also the possibility that it changed over time, but for now, let's just say it looks like this. And what we can see here now is that in some cases, these calls will basically do nothing else than call a so-called mac check macro and give it the same parameters, so the name of the hook and then all the parameters. The only difference here is that there's this credential structure that is additionally given to the hook because the hook wants the credentials, and Apple decided that it's better to already give the call the credentials, even so that the called function could actually also retrieve the credentials itself. It's not really clear why Apple does that. Maybe they only want this whole magic of referencing the credentials once. Maybe they want to move this error-prone operation away from the callee. But in any case, they're just giving the credentials of whoever performed this anonymous mapping directly to the hook itself. So what is this mac check macro? It is one giant macro that looks very scary, but in reality it's quite simple what it does. It basically has internally two lists of Mac policies. One is the dynamic or the static policies, and the other one is then the dynamic list of policies that can be loaded. So what it does first is it loops over all the statically compiled policies, and then it loops over all the dynamically loaded policies. In both cases, it's doing the same thing. It checks if the hook is implemented in the policy, and if the hook is implemented, it will execute the hook and collect the return values and feed them through the mac error select function. The mac error select function is basically just there to distinguish what is the most important error, because one policy module could say something like einval and the other says enomem or something else, and then this mac error select needs to select which is the most important error return value, because that's what we give back to the caller. So in any case, the logic of a mac check is if there is one policy module disallowing it, then it's not allowed, basically. Yes, so we ignore the other macros for now because we condensed this for the advent calendar. But the next thing is what hooks do actually exist. And the nice thing is, in the source code there's this file mac_policy.h that has the table of all the policy operations in there. So this here is policy operations 13. That's a very old version. The problem here is that there's actually nothing inside a kernel that contains the value of this operation version. So that means a kernel driver is never able to actually know what kernel it runs on and if they have a compatible Mac policy ops. That's a very strange thing by Apple, but that's how it works. So basically, whenever you compile a driver against this operation table, they are fixed with this operation table, and they cannot even see if the kernel uses the same one, and so there can be misunderstanding and crashes if a kernel driver is not compiled for the specific Mac policy version. Thing is here that Apple does not want anybody to write anything for that Mac policy anyway, so they keep this private for themselves. But the reality is that the Mac policy is like powering so much security. Even the endpoint security system extensions, they're basically fully implemented based on a Mac policy driver. So this file is even better because it not only contains the list of all the hooks, but it also defines every single hook very clearly with full documentation what the hook is supposed to do and what each parameter is supposed to mean. For example, here we have a vnode check open. So this is when you try to open a file, or mostly a file. And you can see here what you're supposed to return in what case. And this allows you to write basically a driver that would disallow code to open a file. The nice thing here is this is like going deeper than the chaos framework, because in chaos all the file operations were just logging. Here you can really stop someone from opening a file. So this is another one. This here is the vnode check read. It's very similar. You can see that someone is trying to read from a certain file. You can see who is doing it usually, and normally that's also the currently running process. So you can always determine this from the current proc in a kernel driver basically. But you also get here the credentials and stuff like that. So that is this. Now when you know all the policies and you want to write your own driver, or you want to reverse a driver, you need to know where you register these policies, and you do this by calling a function called Mac policy register, and it basically gets a few parameters. The first one is this policy configuration structure. Then you have a handle. This is where you have the returned handle if the registration worked fine, and you can give extra data to some of the hooks. So, and then you have the policy configuration here, and you basically have a short name, then you have a long name. The short name is referenced also inside code. When you call Mac policy system calls, you have to tell it the short name so that it knows what policy to talk to. But the full name is basically human readable full description what this policy is supposed to be. Then it has an array of label names. So the thing is that a policy module can register labels. These labels get attached to objects so that the policy module can store additional information in there. For example, the sandbox policy module will store the sandbox pointer in the credentials label pointer for a process. and that's where basically the sandbox comes from then. And yeah, you also have to specify how many of these labels you need. Normally, most drivers take one. The thing here is there's a hard-coded limit of like, I believe 7 or so in the kernel. More the kernel at the moment cannot handle. So there's basically a maximum of drivers that can request for labels, otherwise you will have trouble. So then you, of course, you have some flags here that's not so important. There's just like load and runtime flags. Oh yeah, the field offset, this is where when your policy module gets a label assigned, the first label slot that it gets assigned is basically written into the field offset so that the policy module knows which label is actually assigned to it. Yeah, and then this here is basically a pointer to a big table of all the operations. And of course, your driver has to fill out all the hooks that it wants. The rest needs to be null so that nothing will happen in these not hooked cases. Yeah, and if you want to find policy drivers on your system, what you need to do is you need to either on iOS take the kernel binary and look for cross-references to Mac policy register, or when it comes to macOS, you can grab through all the drivers basically and also search for Mac policy register. And if you find a hit, then it's likely that you found basically yeah, a policy driver. So on iOS you will find Apple Mobile File Integrity and the Sandbox, and on macOS or OS 10 you would find Apple Mobile File Integrity, Sandbox, Quarantine, Endpoint Security, Apple System Policy, TM Safety Net, and MCXALR. All different kind of built-in policy drivers that come with macOS by default. And of course, when you have a newer version of macOS and so on, you might have newer policies. Same for iOS. Theoretically, there can be anytime a new policy if Apple needs them internally. Yes, and that's it. This is a short walkthrough through what the Mac policy framework is. This is very important to know because a lot of other security features on macOS and iOS are basically rooted on this being inside the kernel. So that's it for today. See you tomorrow for the next door of the advent calendar.